from Ohio State that will be talking about the molecular pathogenesis of CLL.
Thank you. So, I will give you the geneticist view of CLL. And the story I'm going to describe to you now started some time ago when we cloned a gene involved in T-cell prolymphocytic leukemia, essentially all the T-cell prolymphocytic leukemia, which have translocation inversion that involve 14q32. And we were able to clone the gene involved in T-cell prolymphocytic leukemia, and we call it TCL1 for T-cell leukemia lymphoma 1. And the gene encoded probably on 114 amino acids, which is present in the nuclei and in the cytoplasm of early B and T cell. Then we made transgenic mice in which we dysregulated this gene in T cell, and all these mice developed T-cell prolymphocytic leukemia, indicating that really the dysregulation of this gene is the cause of this malignancy. But then we found that this gene was also overexpressed at high level in a variety of B-cell malignancy, including B-cell CLL. And therefore, we wanted to figure out what would happen to B-cell if we would increase the expression of TCL1. And so we made transgenic mice in which we dysregulated TCL1 in B-cell using the immunoglobulin immune enhancer. And all these mice, you heard already this story before, and all these mice at the average age of 12 months develop a CLL. And which kind of CLL they develop, in collaboration with Dr. Chiarazzi, we found that all these CLL were the aggressive form of CLL, and the penetrance was 100%, so all the mice developed this malignancy. And therefore, we speculated that this regulation of TCL1 might be the cause of the aggressive form of B-cell CLL. And I will address the question how this dysregulation might occur. Then we focus on the cytogenetic alteration observed in CLL, and we focused mainly on the most common rearrangement, which is 13q14 deletion, which is observed by cytogenetics in 55% of the cases of CLL. And we were able, by using a number of genetic tricks, to identify the critical genetic alteration which is associated with this alteration. And that was a very startling discovery, because we found that this alteration consists in the deletion of 2 microRNA genes, MIR15 and 16. And then when we look at the loss of MIR15 and 16 in CLL, we looked at about 70 to 80% of CLL have this genetic loss, which indicates that very likely loss of MIR15 and 16 is the driver for the great majority of CLL. And that is associated with the indolent form of CLL, and also observed in indolent CLL that progress to aggressive CLL. So after that, we found that MIR15 and 16 target a gene that we discovered many, many years ago that I call BCL2. And you know what BCL2 does. So essentially, loss of MIR15 and 16, so you know microRNA are negative regulator of gene expression. So a loss of MIR15 and 16 results in overexpression of BCL2, and that might be involved in the pathogenesis of CLL, might be critical to the pathogenesis of CLL. A proof of principle that might be the case is the fact that you all know that ABT199, which is a BCL2 inhibitor, has a dramatic effect on CLL, okay? You get complete remission, and you get also disappearance even of minimal residual disease, which is the proof of principle that if you hit the first genetic alteration, the first genetic alteration that occurs in CLL, you might have a dramatic effect, therapeutic effect. Then we found that the MIR15 and 16 target also MCL1, which is also overexpressed in CLL, and so on. So in the study that I'm going to present to you now, which is not published yet, but will be published soon, we tried to figure out why TCL1 is dysregulated in CLL. And we have made already some progress before in collaboration. This was work of Yuri Pekarsky in my group in collaboration with Tom Kipps and the CRC. And we found that there are microRNA that are lost during the progression of CLL that target the 3' untranslated region of TCL1. For example, MIR29 and MIR181B. In addition, some time ago we published a study in Blood where we follow patients that had indolent CLL that remain indolent for many years, and we had a number of cases of indolent CLL that converted to aggressive CLL. And the difference between these two groups was rather small, because the major difference was the loss of MIR181B, which is a negative regulator of TCL1. So the loss of this negative regulator resulted in overexpression of the TCL1 gene. More recently, what we did was to focus on the 3' untranslated region of TCL1. And in the 3' untranslated region of TCL1, we found a repeat of 28 nucleotides, which are duplicated. You see 3 copies of them. And this is due to duplication. Okay? So we thought that this triplet could be targeted by specific microRNA, and by targeting this 3 separated target of this gene, that could result in degradation of the target messenger RNA and in a block of translation of TCL1. So what we did was, by bioinformatics, to look at possible microRNA that might target these triplets, okay? And we found 4. 4 microRNA are predicted to target this 3 site. And they were this, 3676, and this other 3. Then we look at the expression of this 4 microRNA in CLL with different cytogenetics, in particular 13q and 11q. And we found that, in fact, of these 4, the one that seemed to be targeting TCL1 was probably 3676. Okay? So you see there is a low level of expression of TCL1 when you use MIR3676. So we focus on this microRNA, and you will see there is something quite interesting come out. This work was done, again, by Yuri Pekarsky in collaboration with John Bird and Tom Kipps and others. So a surprise was that this MIR3676 is encoded by a gene which is on 17p. Okay? This locus is about 500 kilobases from p53. But you know, the deletion that you see in CLL at 17p are very large. And there is always, or almost always, a co-deletion of p53 with MIR3776. So in this place, at 500 kilobases from p53, there are 2 microRNA, 3676 and 4521. And here there is something interesting, because we found that these 2 microRNA are embedded in the gene for tRNA, for tRNAs. And one for serine and one for threonine. And so what happens is that the processing of this microRNA is totally different from the processing we observe with most known microRNA, okay? For example, you know, a precursor, you have Droja processing and so on, okay? So in the case of miR3676, you have tRNA for threonine that is cleave liberating miR3676. Then at this point, we look at the expression of miR3676 by real-time PCR, and we find that it's downregulated in CLL. In fact, it's downregulated in all the different cytogenetic type of CLL. You see that the expression is much lower than CD19 positive B cell. But if you look at the different cytogenetics, this slide summarizes the finding. The lowest level of 3676 are observed in CLL with 17p deletion. So this, you know, it's very difficult to see microRNA by northern blot. In general, we use real-time PCR or sequencing or nanostring. But by northern blot, and these are CD19 positive B cell, and you see this microRNA. You see this microRNA by northern only in one case of CLL. So at this time, what we try to do is to perform an experiment that clearly show that the miR3676 target the TCL1. So we did the luciferase experiment, and if you have a TCL1 which has the entire 3' untranslated region, and you see that 3676 shut down the expression of TCL1. If we erase the two sites of the three of interaction of 3676 with TCL1, you see that you have less. You have less inhibition. And if you delete all three sites, there is essentially no difference, okay? Which indicate that, in fact, miR3676 shut down the expression of TCL1, but if you have three sites of interaction, that works much better. In fact, it's a dramatic, as you will see in a second, shutdown. In fact, I never saw such shutdown using with other microRNA, and we work with really dozens and dozens of microRNA. So in this case, we transfected kidney cell with an expression vector for TCL1 and with miR3676 at different concentration. And what we observed that with miR3676, even a very low concentration, we see a completely shutdown of the expression of TCL1. As I mentioned, this level of shutdown is very unusual for microRNA. So finally, we look at the mutation of this microRNA and by sequencing. And we found we have sequenced about 550 CLL, and we found 5 mutants. Okay? And all these 5 mutants were germline mutants. Okay? And interestingly, I don't have a slide for that, we have also sequenced the 3' untranslated region of TCL1 in several hundred cases of CLL, and we found some mutant in which there is a deletion of those 3 sites at the 3' untranslated region of TCL1. So in summary, the sequential alteration in the expression of microRNA that target TCL1 is probably responsible for the overexpression of TCL1 that is quite dramatic in the aggressive form of CLL. So the first genetic alteration in most CLL is the loss of MIR15 and 16 that result in overexpression of BCL2 and other anti-apoptotic genes. And the second most dramatic change is the dysregulation of TCL1 that convert indolent CLL to the aggressive form of CLL. Thank you very much.
So thank you, Carlo. I'd like to now welcome Dr. Coutre from Stanford, who will